Should start now. Mm, Today we will talk about complex integration जी. हमने complex differentiation देखी. Today we will talk about complex integration, how we integrate complex functions, complex valued functions with domain set of complex numbers. But to define this, we need to set some preliminaries, and we need to define some things. And the things that we need to define, let us put them in some heading, subheading of contours. I will start with the definition of an arc. An arc, let me denote it by C, is nothing but is a set of points of the form x, y. Let we can denote the complex number in this way also in C, the complex plane C, such that these points, the coordinates x and y are the functions of a variable, real variable, such that x is a function of real variable t and y is also a function of real variable t, and this t lies somewhere between this interval, closed interval a b, and this t is also known as a parameter of this arc. You look at this thing is nothing but what you are saying, that you have set of points and those points are moving along with t. If you have this interval here a, somewhere here, I cannot plot in this way. Here I have this interval a b, have a function. What's happening? Every point, and let this arc be of this form. Let me change color. Yes, this arc can be of this form. It can be like this thing. It might start from this point here, and it might end somewhere here. And how do we decide its start and end? And this the initial point of this arc has to be the image of x and y at a, and the last point, which is called the terminal point here, this has to be the image point of b, and this is the initial point x a y a. So we give it as a direction that this arc is being traveled in this way. So this is an arc, any function. This is a set of kind of functions, and these are not only the functions, these are continuous functions. I must complete this way, that an arc C is a set of points in C such that x is equal to xt and y equals to t are continuous functions. Continuous functions of t. So this way, this is an arc. Now we will define some types of this arc. But let's look at another way of defining this arc. Or we can also write it as that arc is nothing but it's just kind of function z of t, because complex number can be written as x of t plus I y t. This can be the way to write this, and usually we will denote this in this way. Any arc, this will be denoted in this way, and we fix this kind of notation where this parameter lies between this interval. So now there are various possibilities of this arc. Like first, let's look at it is possible that this z of t1 is not equal to z of t2 for any t1 not equal to t2. In the language of functions, you will call this as a 1-1 function, but if it is an arc, we call this arc to be a simple arc. Then this arc, which arc जो arc ये z function represent कर रहा है, this arc C, which is z of t xt plus iyt a less than t less than equal to b is called a simple arc, or there is another name also to it, which is Jordan arc भी कहा जाता है इसको. This is also known as Jordan arc. So what is this thing that you have the possibility of arcs like this is also an arc. This is also an arc. Suppose it starts from somewhere here and it ends here. This is also an arc. But here what we have that this is not just a minute. Just a minute, I need the minimum. Okay. So what is the problem here? Here the problem is with this point. Here, look at this place here. What's happening here? This arc is crossing itself. When it is crossing itself, that means for certain t1 and t2, zt1 is equal to zt2. So this doesn't qualify the definition of this simple arc. So that means this is not a simple arc. So what is a simple arc? Simple arc is where you cannot have this kind of possibility where the arc is crossing itself. Like you have this to be this is just a simple arc. Any function like let's signify its direction also. Like this is also a simple arc. Now another possibility is there. Another type of the arc where you have this kind of situation that it is possible that initial point of the arc, which is ZA, is same as ZP. For example, look at this arc here. Yeah, look at this thing. I am saying that initial point of the arc is equal to the terminal point of the arc, and let this be the initial point and this be the terminal point. And in such situation, the arc is known as a closed arc. But if zt1 is not equal to zt2 for t1, t2 in open interval AB, that means we are keeping the possibility, we are assuming that ZA is equal to ZP, initial and terminal points touch each other, but these are the only points where the arc meet itself. Elsewhere it doesn't meet itself or doesn't intersect itself. In this case, the arc is known as simple closed arc. Simple closed arc. So this example here is not a simple closed arc. This one, this is not a simple, this is just a closed arc. This is closed. This is not simple closed, but this is not simple closed. So what is a simple closed? Let me write simple closed arc here. So for example, this way. You look at any circle. This is a simple closed arc because circle meets only at one point. It doesn't intersect anywhere else itself. It intersects only at initial and terminal point. So this is an example of a simple closed arc. Simple closed arc, और या इसको कर्व भी बोला जाता है, सिंपल क्लोज्ड कर्व भी बोला जाता है इसको, ठीक है जी, सिंपल क्लोज्ड कर्व भी बोला जाता है. So let's consider some examples. For example, let me consider some what I showed you. I just defined. I didn't express them in parameter form. So let me consider some. We have this thing z of t defined as t plus it when t lies between 0 and 1, and it is t plus I when it lies between 1 and 2. So let us plot this, what it is. What is it? Here it is 1. Let us plot this, how we are going to plot it. And it is 2. So first it is t plus it, it is a diagonal line up to 1. And then after that it is a line. You have imaginary part as a constant. The only thing that is varying here is the real part, z of t. That is, t is varying from between 1 and 2, and I is constant. So I has to be constant. So it has to be a horizontal line. So this thing. This is a arc. This is example of an arc, but it's an arc. It's just it's simple because at no point arc is intersecting itself. And another example you can look at it, the parameter equation of circle z of t as cos t plus I sin t. This is the parameter equation of circle where I fix t to be 0 less than or equal to t less than or equal to 2 pi. So this is a simple closed. This is an example of a simple closed curve or arc. This is a circle with center, origin, and radius 1. How do you know that this is such a thing? You have its center is 0. You look at the modulus of z of t. Modulus of z of t is going to be cos square t plus sin square t square root, and it is equal to 1. So obviously you are having this equation modulus of zt is equal to 1, and this represents nothing but the unit circle with center 1 and radius, center 0 and radius 1. We want or we will be dealing with some further more special kind of curves or arcs where we want these functions. We have arc this c x of t plus I y of t, where this is the parameter interval. What we wish for these functions x and y to be smooth functions. Smooth functions, when I say that this is a smooth function, means that is we have derivative of x exists and derivative of y also exists, and they not only exist, they are continuous They are continuous. That is, when you say that when derivative of x and y exists, we say that derivative of z exists. That is, zt exists and is continuous on this parameter interval. And for being smooth curve, it is not only it is not sufficient to take that the derivative is continuous. We require extra thing, and also we require that its derivative doesn't vanish anywhere. Zt is not equal to 0 for any t in this interval. So any such curve whose derivative is continuous, or you call them continuously differentiable because its derivative exists and its derivative is continuous and it doesn't vanish anywhere, then we say that such a curve is known as, such zt is called smooth arc. We call it smooth arc. So then if we have a smooth arc, then it is possible for us to compute its arc length. How we are going to compute its arc length? We suppose that we have a smooth arc. Let we have this smooth arc z of t a less than t less than equal to b. Then its arc length, I denote it with the symbol L. And when we will be computing arc length of more than two curves, two arcs at a time, then it is better to use L of C, so that it signifies, it tells you that arc length of which curve you are talking about. Otherwise, you have, if you have a single curve, you just use the term L. How you're going to calculate it is being calculated as a to b modulus of z prime t dt. This is a formula to calculate the arc length of any arc. If you write it in an expanded form, it is x prime t square plus y prime t square dt. And let's first calculate the arc length of some a very known curve. Let me calculate the arc length of the circle so that you get to know what it actually is. Let us consider this z of t as cos of t plus I sin t, and the parameter interval is 0 t less than equal to 2 pi. So clearly it is a smooth arc because you differentiate it. You can differentiate it, or both the functions are differentiable, and also its derivative is now where 0. And then its length has to be 0 to 2 pi. It has to be mod z prime t dt, and what it comes out to be 0 to 2 pi. What it has to be cos square t plus not, I have to take the derivative. I have to write first sin square t. It will be sin square t plus cos square t dt, and what it comes out, because sin square t plus cos square t being 1, you have this thing 1 dot dt, and this integral is nothing but this is 2 pi. And remember, what is this thing? This thing is nothing but this is the circumference of a circle of radius 1. So it is nothing but it's not nothing. It is not anything new here that you are calculating. It's something that you already know. So actually circumference is what? Circumference of a circle is the length of the that circular line. So that is the arc length here. But let us look at another important aspect of this invariance of this arc length under the change of parameter. Invariance of arc length under change of parameter. But when we say that change of parameter, you have the parameter interval AB, and your arc is defined. You are considering the smooth arc. Your arc is defined from, let this be z of t. Your arc is defined from this interval to c. It is a smooth arc, and then you call this to be, this is the parameter interval, and t is the parameter. What we want to do, we want to do that if we change the parameter, will it change the arc length of the curve or not? Let us consider another parameter interval CD, and suppose we have a function between these two parameter intervals, this phi. But this phi has to have some properties, if like phi needs to be, phi its derivative needs to be, that means its derivative must exist and its derivative needs to be positive. When we say that its derivative is positive, obviously phi is an increasing function. And not only this thing, we also needs that its derivative is continuous. That means this is continuously differentiable. So under such change of parameter, you get a new arc, the composition function, which is, let this interval be phi of r. You get new function as z of phi of r. But what doesn't change for us is the range of this function is same as the range of z of t. Now we want to establish that the length of the both the arcs, when we consider parameter as t and when we consider parameter as r, the length remains unchanged. So let us look at how length remains unchanged. Let's calculate the length of this composite new arc. So if we calculate the length of this new arc, let me denote it by c, and let us give it the new arc, give a name c phi, just to designate that phi is the function which is changing the parameter. So by definition, it has to be c to d. It has to be d upon, what you do, you differentiate with respect to parameter. Now we have a parameter r, and it is z of phi of r and dr. Use the chain rule within the modulus. So what you have the derivative of z at phi r into derivative of phi of r. Why I am dropping the modulus from phi of r, because derivative is already positive. So modulus of a positive number is always the number itself, tr. Now let us put some change of variable here, because this is the usual integration. Put t is equal to phi of r. This is very right and appropriate thing to do here, because phi satisfies all the properties. As r increases from c to d, your t will increase from, what do you say, a to b, because phi is defined in such a way so that it is, and also we need that phi needs to be onto function there, because so that it covers all of the interparameter interval A, B. Indeed, I must write here that phi has to be onto also. Phi is onto, so that what will now happen that when you start with C and you will reach, it is not necessary that it will start from A or something, but okay, it must cover whole of the interval AB, so that we have this thing here to take the limits when we change this variable t, replacing t by phi of r, we can take A to B interval. So when we put t equals to phi of r, we have the length of this to be equals to, so what will be the limits here when you substitute t equals to p r equals to c, you have t equals to phi of c, and since this function is an increasing and onto, so it must begin with a, so phi of c has to be a, and phi of d has to be b, and you will have z derivative at t times, what is this? This thing is what is d of t? Look at d of t is nothing but derivative of phi and times dr. It has to be d of t. So, but look at the right hand side now. This on the right hand side, this is nothing but this is the length of the arc C. So far, this establishes that if you change the parameter under appropriate conditions, under smooth conditions, I must say, then the length of the arc doesn't change. It remains the same. So I pause here for a brief. If you have any question, you can ask. First of all, let me ask you, can you hear me properly?
So,
Okay, if you have any question, please go ahead.
यस सर, सर जो आपने सबसे पहले आर्क बनाए थे, नोट सिंपल आर्क,
Just a minute. Simple arc, huh?
सर नोट सिंपल वाली भी थी ना एक। हाँ सर, ये
हम्म,
सबसे फर्स्ट वाली, सर क्या ये क्लोज्ड है?
क्या बोल रहे हो, दोबारा रिपीट करना।
जो सर सबसे पहले वाली आर्क है ब्लैक वाली, ये क्लोज्ड होगी?
नहीं, इसमें सिंपल, जो सिंपल की डेफिनेशन है,
हाँ जी सर, ये जो ब्लैक वाली आर्क बनाई है ना, ये भी तो बीच में क्लोज हो रही है ना, फिर आगे लाइन जा रही है।
नहीं नहीं नहीं, क्लोज्ड का मतलब क्या है? क्लोज्ड का देखो ना, क्लोज्ड की डेफिनेशन नीचे देखो। क्लोज्ड हम तब बोलते हैं जब आपके पास इनिशियल और टर्मिनल पॉइंट्स कोइंसाइड करें, बीच में कुछ भी इंटरसेक्ट करे वो क्लोज्ड नहीं होगा। क्योंकि
ओके
ये जो ब्लैक वाली आर्क है ना, ब्लैक वाली आर्क में तेरा इनिशियल पॉइंट यहाँ से है, यहाँ से इनिशियल
यस सर,
पॉइंट है इसका, दिस इज जेड ऑफ ए, और टर्मिनल पॉइंट कोई जेड ऑफ बी है। क्लोज्ड होने के लिए बीच में वो कहीं पर भी क्लोज हो सकती है, जैसे ये दूसरी जो जहां पर मैंने एग्जांपल दी है, ये डबल क्लोज करा हुआ है इसको, तो क्या है,
सर
ये क्लोज्ड इसलिए क्योंकि आपके पास इसका इनिशियल और टर्मिनल पॉइंट कोइंसाइड कर रहा है। बीच में आपके पास आर्क किस तरीके से भी हो सकती है। इट इज पॉसिबल कि आपके पास आर्क ऐसे हो, ऐसे हो, ऐसे हो, लेकिन इनिशियल टर्मिनल पॉइंट्स आपस में कहीं पर भी इंटरसेक्ट ना कर रहे हो। तो क्लोज, वी विल कॉल इट क्लोज जब इसका इनिशियल और टर्मिनल पॉइंट्स कोइंसाइड करेंगे।
ओके सर।
एनी अदर क्वेश्चन? So finally, let me write the definition that we needed. Is the definition of a contour. What is a contour? A contour, or you call it piecewise smooth arc. Contour का दूसरा नाम, we will call it piecewise smooth arc, is nothing but it is an arc. Is an arc consisting of a finite number of smooth arcs, and those smooth arcs has to be joined end to end. They have to be joined end to end. So this is I have considered already one of the example that it need not be smooth as a whole, but it has to be smooth in pieces, and the points where the smoothness is questionable. When I say that questionable means the points where it is possible not to have smoothness, the number of such points has to be finite. For example, let me consider this. We consider this one. This is an example of a smooth arc, a piecewise smooth. This is not a smooth. Why it is not smooth? If anybody notices it, it's good thing, because at this point here, one. This is one here. Let me write in complex form. It is one. At this point where this turn is very sharp, where the bend is very sharp here, this is not smooth. This is not smooth. Whereas elsewhere, right from the origin to this point, it is a completely straight line. It is smooth function, and afterward, this point where we have a sharp bend, and the sharp bend is at 1 plus I1. Afterwards, it is a horizontal line. It is also a smooth. So there is a point where this is not smooth, but elsewhere it is smooth. Or you can also look that it is made up of two line segments, and each line segment is a smooth arc. So it is constructed out of smooth curves. So I must say smooth arcs, two smooth arcs. So any such curve, any such uh, arc which is made up of finite number of smooth arcs which are joined from end to end, then such a arc is called a piecewise smooth arc, or in short it will be known as a contour. So in this is more general form of a arc, so it covers everything. Any smooth arc is also a contour, but it says that if you have number of, for example, I have this, suppose this is smooth arc, I can join another arc with it, another smooth arc. Let me join another smooth arc with it, and let me another here. So everything this appears to you is a contour, is a contour. It consists of three smooth arcs. And what is the problem here, that why we do not say that it is a smooth arc only? Because at the points where we glue together these different arcs, maybe at those points it loses its smoothness. Here it's not possible, but that hardly matters to us. In case of integration matters, this will not affect a finite number of points. Smoothness can be avoided. Is it okay? So this is a smooth arc. Now, what do you say, contour? So we require the concept of these contours arcs to define integration of complex functions, and that integration that we will be defining is a line integrals. In real analysis, you studied this Riemann integration, and you have studied Riemann integrals also. Riemann-Stieltjes integration, but what was there? You already you have studied that integration limits from some point A to B, where A and B are real numbers. That means what you do there, you have the real line only. You don't have anything here. You have a A, you have a B, and you are following a straight line path from A to B. But in case of complex plane, if I have a point here and I have another point here, so it is not possible that every time I have a straight line path from A to B. I might have a path like this also from A to B. I might have a path like this, very complex from this. I might have a path like this, moving this way, this way, this way, this way to reach this. So everything, every possible path that I can have from a point here in complex plane to another point in the complex plane, then the path there is nothing but it's an arc. And we will restrict ourselves to some good arcs, mostly the piecewise continuous arcs. Yeah, but you say we will consider only the contours, so that the arc is made up of finite number of smooth arcs. And then the question of limits from A to B will be addressed once we consider the parameter interval of those contours. So the setting has to be like this. For the definition of a line integral, we have a contour be a contour, and let us designate it its initial and terminal point, and we suppose that it is a contour from the point alpha, initial point, to another point beta, which is image of B. And f we are considering to be a piecewise continuous function. Piecewise continuous function on this curve C. We have this curve. Suppose you have this curve. You have a function here. You have a complex valued function. Take your data. It is a complex valued function. You have a complex valued function. It is piecewise continuous function. Now, piecewise continuous functions means you just keep in mind that if it has discontinuity, it has finitely many discontinuities in pieces. Maybe it has finitely many discontinuities, and if such is the case, if it has finitely many discontinuities, then on from this point to this point on this piece of the curve, this will be continuous, except at this point. Then from this point to Z2, you have another piece of the curve where this function is continuous. Again, if you have a discontinuity at Z3 also, then from piece Z2 to Z3, this function is continuous. So it is continuous in pieces on this curve. So it is defined on this curve and it is piecewise continuous. And obviously, this is a complex valued function. It will have real part and imaginary part. But how we are going to define its integration? So we are going to define its integration as, but remember, you have this curve, you have this contour. So what is this contour? This contour has a domain, certain parameter interval A, B. So how we are going to define the line integral? We are going to define the line integral over this contour C. Right, contour C here, notation is f of z, dz, and the definition is integral f of, because this we are taking z from C, but this C, every point on this C is a parameterized point. You can write it as z of t. So when you write z of t, f of z of t becomes a function of real variable t, and dz of t, dz of t you can write it as derivative of z at t times dt. Now you are integrating whole of this function with respect to a real variable t, and real variable is varying from a to b. So you can what is this thing? You might get confused that okay, what is this thing here? If you take f to be, if f has two parts, one is real part and another is imaginary part, and u and v then are real functions. And if you further write it as, you can write it as uh, a to b. I will drop just for space deficiency, because of space deficiency I will write it as u. It will be a function of something x of t, y of t, plus I times v of x of t, y of t, into what is z prime of t. Z prime of t has to be x prime of t plus I times y prime of t dt. And if you multiply these functions, you multiply this, I'm going to write it here only so that I do not have to go to the next slide. Let me write here what it is going to get. You multiply these functions u plus iv and x prime plus I prime, you get u dot x prime minus v dot y prime. You get one this function plus I times you get u dot y prime plus v dot x prime into dt. So when you consider integral, you have to integrate this function first from a to b, and I times you have to integrate this function a to b with respect to t. So now you have two integrals, and you are taking the integration of real functions now. U is a real function, x prime is a real function, you are taking the integration of real function. So you have to use the integration of real valued functions to define the integration of complex valued functions here. So this is exactly how you define the line integral of a complex variable. Do you have anything to ask?
No, sir.
So let's make it further clear. It will be if I calculate what you say, integral of sum of one of the functions. Let us do this thing. Let us compute this integral c z square. Just a minute. This needs to be pen. Z square dz, where c is this line segment from 0 to 2 plus I. You have this line segment. What is our its parameter that has to be found? So first let us look at what is this c. C is a line segment. Let it be a point. C is a line segment from point this to here. So C is a line segment. C is a line segment from point origin to another point. So टू I को आप कोऑर्डिनेट फॉर्म में लिखे रेक्टेंगुलर कोऑर्डिनेट्स में it is 2, 1. So what is the equation of this line? If we use y coordinate as a parameter, then I can write this equation as then I can write this equation. Then the equation of this line, आप 2 point form of line की equation से इसको derive कर सकते हैं. It is not a difficult thing. X equals to 2y. So let's use parameter to be y. So when you take parameter to be y, what has to be the minimum and maximum value of y? It has to be between 0 and 1. So then we have when we have to integrate z square over c, then I can take z square to be function of z of y. It has to be 2y plus what do you say, I, y. This has to be the arc that you have, because z of y is equal to x of t plus I y t, and here y is a parameter, and in place of x you just put 2 of y, and y is varying between 0 and 1. So you get the equation of this curve that is given to you, and now you have to integrate this c. You have to integrate this c. By definition, it has to be integral of c z square dz. It has to be equal to integral from 0 to 1. It has to be, what do you say, z of y whole square into z prime of y into dy. It is 0, 1. You calculate this square of this zy. Square of this y, it has to be 2y plus iy whole square. What is the derivative of this zy? It is 2 plus I. You are differentiating with respect to y. You have the parameter 2 plus iy dot dy. And if you want further simplification, you bring out the y square. You will be left with 2 plus I square into 2 plus I dy. What it is 2 plus I whole cube being constant. You bring it out 0, 1 y square dy. And you just compute it as a real integral 2 plus I whole cube, and it has to be y cube 3 integral 0 to limits from 0 to 1 2 plus I cube into, it has to be 1 by 3. You can further simplify it if you expand this 2 plus I cube, and this is the way you just compute. The important thing here is you need to know the parameterization of the curve that has to be there. Do you have any question? Hmm?
No, sir.
Okay, ask me. Okay then. So now I'm going to stop with a statement. I have written it as a in the form of a theorem. It just sums up some of the properties that we require. We will be talking about more of the properties, but again we have to go to the analytic functions. But first, for a piecewise continuous function, I will sum this next theorem will sum up some of the properties, and the detailed proof you will get in the it doesn't require, its proof doesn't require any much effort. So I have written in the notes, you can get it from there. I think it is no need, and if you find any flaw there or any problem there, you can ask me in next lecture. So what is the context? You have a contour, and this is the parameter interval, and we have two piecewise continuous functions, the piecewise continuous functions on C, then the following holds. Oh, what is this thing? It got highlighted. First, integral of negative of C. I will define what is the negative of a contour. F of z dz is equal to minus C of f of z d of z. If you multiply this function with any constant and integrate, take this line integral over C, then the constant can be brought outside C, All these things follow from the definition of, of the integral, just line integration, nothing else. And you take the sum of two functions and you integrate them over curve C. You can integrate them separately as well. The result will be the same. Not only for sum, for difference also, but not for product or division. And further, if C is composed of two contours, C is made up of two contours like this. You have one contour, just color selection, and maybe there's another piece from here, and they are made up of here. They are glued together here at some point. Alpha beta 1 is equal to alpha 2, and suppose it starts from alpha 1 and it ends at beta 2. Then line integral our whole of the contour C can be decomposed as a line integral. Let this part be C1 and this part be C2. C1 f of z dz plus integral C2 f of z dz. We don't have any trouble. And another important thing that the proof of which I will tell you here is the estimate of the modulus of the line integral. This is fz dz over c. The estimate of this is given by this relation, modulus of fz. How estimate of the modulus of the line integral is related with the, but here you will get to know this thing. So all other things up to D that were there, they just follow from the definition, and you few of them are proved in notes also. So what is what seems to be a bit non-trivial is this part here, where the modulus of the line integral of a function is less than or equal to the line integral of the modulus of f and modulus of dz. So I will prove this thing for you here. Let me prove this part. So I have two possibilities. One, that this is 0. If it is 0, then this left hand side will be 0 and its modulus will be 0, and right hand side is a greater than or equal to 0. So then equality is trivial. So there is nothing to prove. There is nothing to prove. So assume with that we have to prove when this thing is non-zero. We assume that fz dz is non-zero. So this is a non-zero complex number, and non-zero complex number has a polar form. Consider its polar form. Consider its polar form, and let its polar form be it's a complex number, and it is a non-zero complex number, so it has a polar form, and let it is be. And where r is what is r? Where r is its modulus. R has to be its modulus, and theta is its argument. So what I am going to do, I am going to solve this equation for r by multiplying this with e minus I theta, and e minus I theta being constant can be taken inside the integral. So I am going to get r equals to integral c e to power minus I theta f of z dz. So that means r is a real number. So on right hand side also you have the real number. I can write it as, which implies that I can write R as real part of this thing, because R is a real number. There is no harm in writing this. E minus I theta f of z dz. But it can be verified very easily that real part of f of z dz, its integral is same as real part of integral of fz dz. So with this, I can write it as integral of c. It is real part of e minus I theta fz dz. So there is a relation between real part of a number and its modulus. And what is that relation? That real part of any complex number is always less than or equal to its modulus. Is less than or equal to its modulus. So using this for here, I can write it as, and also another thing in case of real value, because now the integration is of real functions, because I'm taking everything real part, there is nothing complex, so I can use the comparison of every sort here. That is possible in case possible to do in real numbers. So in case of real functions, the integration of f of x dx is less than or equal to integration of g of x d of x whenever f of x is less than or equal to g of x. So now I have two functions. One, I have I can take one function to be real part of this thing, and another as modulus of this function. So I can write it as to be less than or equal to integral modulus of e minus I theta fz dz. Okay. Uh, so if you feel still harmed, still confused with it, what you can do, you can write this limit a to b, and what you can do, you just use the parameterization of c here, just it becomes more clear. E minus I theta, I can write it as f of z of t into dz. I can write z prime of t into t of t. So what is the modulus of ei theta? Since this is a product of complex numbers, modulus of ei theta is 1. So we are left with a to b modulus of f of z of t modulus of z prime of t dt. And now giving back everything to it is c modulus of f of z mod of dz. Because dz, I can write it as z prime t dt, and mod of dz, I can write it as modulus of z prime t dt. So this is here. So this is the what do you say, the left hand side, right hand side. So left hand side is r. So in nutshell, what you have, let me clear this text from this side. I have adjusted all the boards. I have to complete it here. So what is r? R was modulus of fz dz. This is r, and r came out to be less than or equal to integral over c mod fz dz. So this is what we say that we needed to prove the estimate. And as a remark to this, if your function fz is bounded on c, then look at this thing. I can write c mod of fz mod dz to be less than or equal to m, because function is bounded by m, c mod of dz. So if you consider the parameterization, if you take the parameterization, it is a to b mod dz will be mod of z prime of t into dt. So now what is multiplied with m is nothing but the length of the arc. So in that case, your value of integral mod fz dz comes to be less than equal to ml. This is also known as an ml estimate when the function is bounded. But if you take the function to be continuous function and it is continuous function on an arc, then definitely arc, what is this? It becomes a composite function from parameter interval. Let me write it here just to finish off. When you consider you have this interval, parameter interval, you have a function. This is z of t to some arc here, and from here you have a function f. But when you consider this function over C, that means you are considering this composite function. But this, if it is continuous function, and then you say that this composite function is continuous function on this compact interval AB, and this is compact interval, and you very well know that continuous functions and compact interval are always bounded. So that means in case of continuous functions, you do not need to assume this m exists. It will be always there because continuous functions and compact intervals or compact sets already you know that they attain their maximum there. So this estimate will always hold for continuous functions. In particular, for our setting, this estimate will always hold for analytic function in whatsoever curve you take the line integral. So this will be vital estimate. This is called ML estimate. So I stop here. If you have any question, you can ask for 1 or 2 minutes. Then I will stop. You have any questions?
No, sir.
So we had only 20 or 90 students today, but okay. Okay then. See you tomorrow.